Hello. Um, Hello, everyone. So welcome to QIP 2025, and welcome to Raleigh. So this QIP, as you all know, is jointly organized by Duke and NC State. So let's thank the organizers and the program committee for all their effort for the past few months. So this weekend we have 4 tutorials, and the main part of the conference starts Monday morning. One small request, so as people settle, this room I think is a bit smaller than the number of attendees and some ratio like that. So it would be helpful if people just move towards the middle, away from the aisle, so as people come in, they can move. So just please help us with that. And second, when you have questions, please don't shout it out, just raise your hand. We have people with mics in orange in orange shirts who will come by and they'll give you the mic. This is just to ensure that the questions are captured in the recording. Okay? So that's that. And anything else? Right. So there is water right outside. There is water filling fountains. And there's water bottle filling fountains right outside. Water fountains near the washrooms, which are on either side of this corridor. So you can help yourself with that. So first up, we have Cambyse Rouzé from India about quantum Gibbs sampling. The session will be for 3 hours, 1.5 hours, a half-an-hour break, and another 1.5 hours. So that's 9 to 10:30, and 11 to 12:30 with the break in between. So without further ado, let's give it to Cambyse.
Thank you very much for the kind introduction. And I would also like to thank the organizers for giving me the great opportunity to present a research topic, which I am very fond of, which is this topic of Gibbs states and how to prepare them. And this is a topic that has started a long time ago with great contributions by mathematical physicists from the early 70s and even before. So trying to condense this in 3 hours is not an easy task. So what I decided to do instead is to give you some material, especially for those of you who might not have heard about these systems before, for you to be able to essentially attend some of the great talks that we will have on this subject during the conference week. And if you are more interested, to hopefully also take part in the research. So I'm essentially roughly dividing this tutorial into 2 parts. So in the first session, I will give you some motivation for what these systems are and why we actually care about them in our field. And then we will move on to 3 specific quantum algorithms for the preparation of those states. So I will give you some circuit descriptions. And this should keep us busy until the break. And once we reconvene in the second part, I will move slightly away from this, let's say, purely quantum algorithmic considerations and try to better understand from the complexity theoretic point of view whether or not these systems are easy to prepare, and in which cases they are easy, and whether we can hope for some signs of advantage in trying to prepare those systems using quantum computers. And then towards the end of this tutorial, I will give you some methods to actually control the time it takes for those algorithms to converge. Okay, so I should also say from here that please feel free to interrupt me at any time. I would be very happy to try to answer your questions. Okay, so let's start with some motivation. So what are these Gibbs states and what are they good for? And one simple way of introducing those systems is by going back to the actual task of simulation of quantum systems. So this is one of the major, maybe first tasks that we hope our soon-to-be scalable quantum computers will be able to help us with. And for me, a quantum system will be a many-body quantum system, which is made of n particles. And for simplicity, I will even assume them to be qubits. So they all come with their own 2-dimensional complex Hilbert spaces. And then once you put those qubits together, they will start interacting. And interactions mathematically will be described by subsets of your set of qubits, lambda here, together with some Hilbert space, curly h lambda, which is nothing but the tensor product of all the single particle Hilbert spaces, which correspond to those particles interacting at once. And then once you're given these Hilbert spaces, you can define Hermitian matrices, h lambda, which model what you believe is to be the actual interaction within the system. And here we'll already make some physical assumption, namely that the sets that I will consider, those interactions, will be concerned with only, so particles within one interaction will actually be a constant number. So I don't want to assume that all the particles of the system will interact at once. So this is kind of a locality assumption that I'm making here. And once you're given those interaction terms, you define the Hamiltonian to be the sum of all those terms. Okay? So once you're given the Hamiltonian, you can start discussing what you actually mean by simulating those systems. And there are different ways to introduce the simulation task. The first kind of way you can define this is what I would call a dynamical property, where you say you initialize the system in the all 0 qubit state, and then you evolve according to Schrödinger equation associated to this Hamiltonian. And the task is, for instance, given some observable O, to compute or approximate the expected value of this observable in the state that you have at time t. Okay? So this is one task that we believe our classical computers will have a hard time trying to get, simply because away from, let's say, perturbative regimes, very small times where maybe you can do something clever, away from those regimes, the only thing that we know how to do is to just perform the diagonalization of this exponential and then just matrix multiplication to get those overlaps. And this kind of subroutines typically scale polynomially with, with the size of the system, but since the system is of size exponential in number of qubits, you see directly that this is going to be very hard for classical computers. On the other hand, quantum mechanics is performing Schrödinger equation on the everyday basis. And since our quantum circuits are somewhat discretized versions, time discretized versions of Schrödinger equations, it's quite intuitive to believe that they should be good at performing such a task. And in fact, this was put into an actual algorithm by Lloyd in the 90s, who came up with an efficient way of discretizing these continuous time evolutions. And since this early contribution of Lloyd, people have been finding better and better, more and more efficient ways of doing this task. And now we have by now some polyoptimal ways of actually getting estimates on those quantities. So this is one way to define the simulation task. But another way you could define it is in the following, what I would call static sense, where now you have to think of your system not being closed, but actually in contact with its own environment at a certain time t equals 0. And then you make the system and the environment evolve together for some time. And what statistical mechanics tells you is that it's very likely that through the exchange of heat and energy between the system and the environment, at some point the system will reach some equilibrium state with a temperature that will be imposed from the environment to the system. And the state that you will end up with will be what is called a Gibbs state. So this is a convex mixture of energy eigenstates of your Hamiltonian with weights given by the following, what are called Boltzmann weights, so exponential of minus beta times E, where beta here is the inverse of the temperature that the bath or the environment is imposing on your system. Okay, of course, for this to become a good state, you have to normalize it. And the normalization constant is what is called the partition function. It's a function of beta, function of the temperature. And it actually also plays an important role in the description and understanding of those systems. So I'll come back to this a bit later. And so here the statics task would be potentially, for example, to compute or approximate thermal averages of certain observables in the Gibbs state, or, as I just mentioned now, approximating the partition function, which is a quantity that you want to learn more about. So at this point, you could say, well, this static task looks a bit similar to the dynamical task. On the one hand, you're given h and t, some time parameter. You want to compute some averages. On the other hand, you're given h and beta, and you also want to compute some averages. There is actually a huge difference between these two tasks in that in the dynamical picture, as I told you, this is always efficient. Quantum computers can always approximate those quantities. The question is more, how efficient can you do this? Whereas in the static task, as we will see later on, there are some parameters, some temperatures and Hamiltonians for which you should not expect even quantum computers to be able to achieve the task. So there's a discrepancy between those two pictures. Nevertheless, they are not completely hermetic to each other. And as we will see when we actually come up with algorithms for preparing Gibbs states, we will very often rely on subroutines which essentially amount to constructing time evolutions. Okay. So before we get to those algorithms, let me briefly tell you a bit more about why we care about those Gibbs states, and actually we care about them beyond physics and statistical mechanics. One place where they very naturally appear is in theoretical computer science, when you are required to compute certain potentially very hard combinatorial counting problems. So here I'm giving like two figures of graphs with vertices which are colored. So I want to think about graph coloring problem, which is the problem where given a graph with edges and vertices, you want to find in a set of labels, some colors, you want to find the number of ways you can actually color your vertices so that no edge would have at its both ends the same color. Okay, so this is a combinatorial counting problem. And in fact, you can encode the solution to this problem into the partition function of a classical Gibbs distribution, so whose Hamiltonian will be diagonal in the computational basis. And the Hamiltonian you can choose will be the function that, given some coloring configurations, will just count the number of edges which do not satisfy this constraint, so for which the edges, for which the end vertices will have the same color. Okay, so it penalizes those not allowed configurations. And then it's not too hard to see that for this Hamiltonian, the partition function, when the temperature goes to 0, will actually converge to the solution of this problem. Okay, so this is a very simple way of encoding theoretical computer science problems into Gibbs states, in this case, Gibbs distributions. Another place which I have very briefly mentioned already before is an application in material science. So here I just give you a figure of what is called a phase diagram of a certain type of cuprates. So these are kind of materials that have those very interesting properties when you cool them down at low enough temperatures. So here in this diagram, you have some parameterization of your Hamiltonian on the x-axis and the temperature on the y-axis. And you see this region in green, which is, I don't know if you can see this, it's written superconductor. So this is a region that has this property of, where the material has this property of being a superconductor, meaning that it offers no electric resistivity. So of course, for applications, this is very useful throughout engineering. And the goal here is to better understand the boundaries of those regions. Typically, what you would like to find is an optimal range of parameters for your Hamiltonian, at which you would still remain a superconductor at the highest possible temperature. Because cooling down systems is very expensive, so you would like to optimize over the temperature you have to reach and still keep this property. I will also briefly mention two other applications, which actually I will come back to later on. So the first one is in the certain convex optimization problems. You can actually use as subroutines quantum Gibbs state preparation algorithms to solve those problems. And one last thing that I just want to briefly mention is also some application in machine learning that came up in the recent years, where the idea here is to parameterize your Hamiltonian with some range of parameters, and then just to use this as a model for machine learning where you want to optimize over those parameters, for example, to minimize some loss functions, say some average energy. And here you may have already heard about variational quantum algorithms, which kind of look similar at first glance, where you have a parameterized circuit which outputs some states, and you want to also optimize over the parameters of your gates in order to achieve this minimal loss. But variational quantum algorithms are well known to have some big problems, typically these Barin-Platos problems, where you can show theoretically that the gradients that you would need to compute to know the direction of steepest descent, if you want to minimize a function, those gradients will be exponentially small in the number of qubits in your system. So it will be very hard actually for you to find out which direction you should follow to optimize those functions. It seems like this kind of Barin-Platos problems may not actually appear when you parameterize your model by Gibbs states. Okay? So that means also that, of course, this hinges on the fact that for this application, but for all the others as well, that if you want to be able to perform all those tasks, you have to find some way to prepare Gibbs states, okay? Which is what we want to do today. So before we move on, let me give you some more intuition coming from information theory. So for this, I would need some entropic measures. So the entropy of a state, the von Neumann entropy, which is minus the trace of rho times log rho. And I will also need to use here the relative entropy between two states, rho and sigma. So the trace of rho times log rho minus the trace of rho times log sigma. This measure will come up later on during the second session. But for now, I just want to use this property that it is a non-negative quantity of its two arguments. Okay, so it's always positive. Unless rho and sigma are the same state, then it would be equal to 0. And now among my set of n qubit states, I will only consider those states which share the same average interaction terms. Okay, so the energy that I impose on all those states is the same. The average energy will be the same. And between those states, now I will consider the difference between the entropy of the Gibbs state, which shares exactly the same energy, average energy as those other states, and any other state in this class. Okay? Now, since the Gibbs state has this exponential form, you can easily compute or express the entropy of it, which will give you the contribution of, which will be the sum of two contributions. The first one, which is the trace of sigma times h, so the average energy of the state. And then you have some other contribution that comes from this logarithm of the normalization factor, the partition function. And now, since I impose that my state sigma and my state rho have the same average energy, I can just replace the trace sigma h by the trace of rho h. And I can then recombine these expressions into getting exactly the relative entropy between rho and sigma. And since this quantity is non-negative, as I said before, that directly tells you that among those states, the Gibbs state is the one that has the highest energy. Okay? So this is a principle called the Jane's maximum entropy principle, of the name of the person who came up with this in the 50s in his study of statistical mechanics. And one way to think about what this really tells you about Gibbs state is that if you're given a system and you know nothing about the system, the only thing you know is the average energy of your system, then the best guess for you for the state of the system would be the Gibbs state, because this is the state that maximizes your lack of knowledge about the system. So you will be the least biased when you choose the Gibbs state to model your system. Okay? But beyond this, say, fairly philosophical questions, actually the Jane's entropy principle, maximum entropy principle, can be actually used in practice into solving certain types of optimization problems. So here I want to think about what are called semi-definite programs, or SDPs, which are problems which appear throughout science and engineering, and also in our field, in quantum information theory. They are very useful ways of rewriting entropic or approximating entropic or measures of distinguishability between quantum states. And so these problems can be defined in the following way. So you're given a bunch of matrices, C and some other matrices AJ, which are sparse. I assume them to be Hermitian and of bounded norm. And you're also given some parameters, Bj. And here the task is to maximize the trace of C against some state rho, subject to a bunch of constraints. So meaning that the trace of each of those other matrices AJ against rho should also be below the parameter Bj. So you have some linear constraints on your optimizers. And since I told you these kind of problems appear everywhere in science, people have tried to come up with classical ways to compute or approximate those optimization problems. And I don't want to go through like the actual way that these methods work, but I want you to just remember that each of these classical methods to approximate the optimal value of the problem will always have a runtime that scales at least linearly with the size of those matrices. Okay, so if you think of this size as being exponential in the number of qubits, if your problem is to understand some physics with systems which are made of n qubits, then you see that, again, this will be very hard to approximate those optimal values classically. Nevertheless, we can actually use Jane's principle into understanding this problem slightly differently. So now let's assume that we have a state rho, which we know is an optimizer. And then let's take a Gibbs state sigma, which I will impose satisfies exactly the same, so has the same trace against C and against all of these matrices AJ. So I know there should exist some Gibbs state which will have this property, and the Gibbs state will be the exponential of a linear combination of all those constraint matrices. Okay? So if you do this, then you know that sigma will also be an optimizer because it has the same trace as rho, and it will also satisfy the constraints because, again, it has the same trace as rho. And now that by doing this, you have reduced the problem of trying to find a very, very large matrix to optimize the problem to the one of finding just a bunch of parameters which will scale with the number of constraints. So you just have to find those parameters lambda j here in this exponential, and you know that there should exist some that would give you, again, an optimal value. And so this idea, or this way of reducing the problem to the problem of finding some parameterization of a Hamiltonian was taken seriously by a bunch of people here, and they actually now realize that you can use Gibbs sampling, so Gibbs state preparation, as a subroutine to solve in a quantum manner the same SDPs. Okay? And the runtime, the best runtime that we can actually get now is something that would scale like linearly with the time that it takes for your Gibbs sampling algorithm to prepare any of these Gibbs states for all those parameters, lambda. And so this tells you that if you could find a way to first prepare any of those Gibbs states on a quantum computer, and second, if you could find a way to control this time it takes for these subroutines to converge, that potentially would give you some advantage over classical methods. Okay, so now we will actually roughly follow these two questions in these two sessions. In the first session, I will actually tell you how you construct those Gibbs samplers. And in the second session, I will give you some tools for analyzing the runtimes. Is there any questions so far? Okay. So here's the actual problem we will be considering for the next 2 hours and a half or so. So I'm given as an input a number of qubits, n, some classical description of some interaction terms, some Hermitian matrices H lambda on your system, some inverse temperature beta, and some accuracy parameter epsilon. And your task now is to output, using a quantum computer, a state, sigma tilde, which you can ensure to be epsilon close to the Gibbs state corresponding to these parameters in trace distance. Okay? And why do we choose the trace distance? It's a very nice measure of distinguishability between quantum states. And the reason why we care about trace distance here and constant error in trace distance is because once you have this, by construction, by definition, you know that you can approximate thermal averages of bounded observables. And you can even consider traces of sigma times some observable that would be potentially evolved according to some other Hamiltonian H prime. And now you go to your favorite physicist, and they will tell you that these are actually the quantities you want to approximate, because they would actually tell you something about these phase diagrams that we have discussed before. So you would actually be able to understand what is the boundary of this superconductor phase if you have access to those parameters. They would also tell you ways to compute partition functions. We will see this later on, how we can reduce the problem of computing partition functions to the problem of sampling certain Gibbs states. And they can even tell you something about the entanglement profile of your state at thermal equilibrium. So they give you, anyway, a lot of information about the physics of your system. So now we will actually spend the last, the session constructing circuits to precisely perform this task. We will see 3 of them. And as you will see, they will somewhat build upon each other. And if time permits, I will also tell you something about how this last algorithm we will see actually can be connected to the actual thermalization process that we think happens in nature. OK, so let's start with the first algorithm, which is due to Poulain and Vogtjan. And here we'll make some further assumptions, which are non-physical, but which will make it much simpler for me to describe the algorithm. So first of all, of course, I can always assume that the Hamiltonian is it is alpha-joint, so I can decompose it in its eigenbasis. So you can write it in terms of eigenvalues Ex and eigenvectors psi x, so eigenstates. And I will assume that the energies Ex of your Hamiltonian can be described with only r bits of precision. So by this, I mean that if you normalize these energies by 8 times the norm of your Hamiltonian, then you could actually write this in terms of bit strings of r bits. Okay, so this is not actually what happens in physics. You would actually be able to, you could have any kind of real parameters here, but for simplicity, I will assume that. Okay, so those bit string descriptions I will denote by epsilon x. And now this algorithm of Poulain and Vogtjan actually relies heavily on your ability to perform what we call quantum phase estimation. So this is an algorithm which I believe all of you have seen before, but let me just give you some pointers. So the idea is that this circuit would allow you, if you plug in one of those eigenstates, to get some access to the energy associated to this state. So what it would do is it will initialize some ancillary systems in the plus state, which I will call energy registers. And then it will output the tensor product of the same state you plug it in, and the computational basis state that describes the energy of that state. And so I won't go through the details of how this works. It relies on some quantum Fourier transform as well as on controlled Hamiltonian dynamics. I just want to again highlight that here you see already a first place where your ability to perform Hamiltonian dynamics will be very useful into preparing the Gibbs state eventually. All right, so how do we use quantum phase estimation here? Now we take two copies of the system, and we initialize them in their Maximilian entangled state, okay, so which I can always write as this linear combination where the second register here, I will take it to span the eigenbasis of the Hamiltonian. This I can always do. And then on the second leg, I perform quantum phase estimation. So the state that you would end up with at the output of this first layer would be a tripartite state where you essentially label the energy of your eigenstates. And then you append one fourth register, which you initialize in a single qubit state 0. And on this fourth register, you will do some rotation controlled by the energy register by an angle whose sinus is given by the square root of the Boltzmann weight here. Okay, so exponential of minus beta e over 2. So at the end of this second layer, then, what you end up with is a four-partite state, which for each x will give you a linear combination of zeros and ones, where the amplitude in front of the zero state here is, again, proportional to this square root Boltzmann weight. Okay? And now let's assume that you measure this last register and you obtain 0. So what does this mean? This means that the state will collapse into this contribution. And you can actually compute what the state looks like. It will look like exactly this. So it will be a linear combination of eigenstates with weights given by nothing but the square root of the eigenvalues of the Gibbs state. Okay, so you're essentially ending up with a purification of your Gibbs state here, which also means that if you were to discard the first and the third registers, you would actually have built or constructed the Gibbs state on the second register. So that's great, because this is exactly what we wanted to do, but this, of course, comes with the caveat, which is that the probability of measuring 0 here is very small. So you can compute this probability, and what you really get is that it will be equal to the ratio of the partition function divided by the dimension of your system. Okay? So now, unless beta is very small, so unless you're actually very close to infinite temperature settings, this will actually decay exponentially with the number of qubits, which also means that if you were to actually know that you have prepared the Gibbs state with constant probability, you will need to redo this an exponential number of times. Okay, so you can do something slightly better than this. You can actually use amplitude amplification that would allow you to bring this weight closer to 1 here. And this you can do with quantum circuits, which essentially amount to a number of layers or gates that scales like the square root of the inverse of this probability here. Okay, so this will scale like 2 to the n over 2, essentially. And if you were to do this, then you can plug this runtime into the quantum SDP solver I mentioned before. And you see that this SDP solver will then run 2 times 2 to the n over 2 as well. And then you can compare this with classical methods we have also seen before. And you see that already here we have gained some square root speedup. Okay, so Groover speedup, of course, are nice, but we would like to have exponential speedup. So the question now is, can we do anything better than that? Any questions for that? Okay, if not, we will continue.
Right, sorry. So for this algorithm, it seems that you also have another additional register that's like not restored to 0. Does that cause some problems?
Another register?
Like the third guy, right? So like you say psi-phi and there's an epsilon, like there.
Yeah.
So that I would assume that would cause some problems if, say, I want to like do other stuff because there's another entangled like junk register now.
But so if you were to look at the reduced state, you agree that you get actually the Gibbs state, right? If you just discard this register. So this anyway gives you more information than the Gibbs state itself.
Yeah, but the question is usually when you have another register, do we need to spend resource? Say we want to use this algorithm as some quantum subroutine or do some other stuff, then in many cases we would still want to restore it back to 0 to put it in some program, right? Depending on the application.
Oh, so here we wouldn't care about this, I would say. But
Okay, thank you so much.
Yes, sir, question.
Another question?
So in terms of the SDP problem,
I
yes.
don't see you.
Yeah, it's here, on the left.
Ah, okay.
Hey, so in terms of the SDP program that you described before, what would the high temperature regime correspond to?
So for the SDP solver here, actually what these algorithms I briefly mentioned, actually they require you the ability that you actually perform Gibbs sampling up to polynomially large beta, so polynomially small temperatures. So it's actually an interesting question whether we can get some additional speedups by imposing high temperature, but this is unclear.
Quick question. So can you remind me, like, what do you mean by a sparse SDP?
By sorry?
Sparse?
The matrices, they will have lots of zeros, essentially.
Okay.
Okay. Now the idea is, can we find some other ways to more efficiently prepare those Gibbs states? And here I think it's very useful to actually try to get some intuition from what classical people have been trying to do over the past 70 years. And among the methods that they have at hand, actually one that seems to always rule them out, all the others, is the MCMC method, so the Markov chain Monte Carlo method. And let me just give you the kind of main important steps in such method, because this is exactly what we'll try to extend later on. So in the MCMC method, you're given a process, a probabilistic process, that is described by some transition matrix P. And your goal here is starting from any distribution row. Say you start with some peaked Dirac distribution around the 0 state. And by running this chain, you end up with something with some random variable which should be distributed according to a law that is very close to the one of the target Gibbs distribution. Okay? So of course, already here you need some requirements. The first one being that this transition matrix can be efficiently implemented. Otherwise, you have not gained anything. The second requirement would be that in the best case, you could actually show that this distribution is a fixed point of your chain, so that you know that you may actually converge towards it. But you may like to also have some other very good properties, which are not required per se, but which make the analysis of these methods much simpler. The first one is what I would call primitivity of those chains, meaning that there is a unique state towards which you converge, a unique distribution towards which you converge. And this we can impose easily by assuming some things about the transition matrix. And the last property, which will turn out to be very useful classically, is what I call the detail balance condition, which is this condition that if you place your train at equilibrium, so you have already reached the Gibbs distribution, then the probability that the chain jumps from some configuration X to some configuration Y is equal to the property of jumping from Y back to X. Okay, so it's in some sort of symmetry condition on your chain. And it's so useful because, first of all, it implies directly that sigma will be a fixed distribution, so you have this for free. And also for analysis reasons that we will come back to later, it's actually also useful to have this property. Okay, so let me give you just 2 examples of such MCMC methods which actually satisfy all those good properties. The first one is the very well-known Metropolis algorithm. So to describe it for you, I need to describe what the transition matrix is. So it will be the Hadamard product of 2 contributions, some symmetric matrix sigma, which is, so by symmetry, then since it is symmetric, that means that it will satisfy the detail balance condition with respect to the uniform distribution. So that one will be the fixed point of this matrix, which is not the one you actually want to converge to. So you have to amend this by multiplying this contribution by some other contribution gamma xy, which in the case of Metropolis takes the following form. Okay, so what this actually means is that what sigma does, let's say it proposes some jump from X to Y, and then gamma will check whether the jump should actually occur. Okay, so what gamma does is that it looks at the energy of your system before the jump and the energy after the jump, so Ex and Ey, Y being after. And then if the energy of y is lower than the one of x, it will always accept. So you will necessarily have to go from x to y. And otherwise, it will still accept with a probability that ends up being exponentially dampened as a function of the difference between those energies. Okay, so if you write this gamma matrix as a function of EY minus EX, this is the kind of plot that you get, and you see that it is highly biased towards jump towards lower energies. Okay? And this is done in such a way that by construction, the detailed balance condition is satisfied. So you know that with this gamma, you will actually converge to the Gibbs distribution. So some other MCMC method, which might be more known to the physicists in the audience, is Glauber dynamics, which follows a very similar rule. So it's, again, I still have to tell you what the transition matrix is in this case. It will be, again, some Hadamard product between some symmetric contribution and some matrix gamma. And here, the symmetric contribution is just a way to decide or to choose one site or one bit over your system. So let me describe this with a specific model, the Ising or the ferromagnetic Ising model, whose Hamiltonian is just the sum over all the edges of a graph of the product of the spin configurations at each end of one of those edges. So here on the vertices, I have spins, so either -1 +1. And this Hamiltonian is essentially favoring configurations that are penalizing configurations where you have many spins that are not aligned as ends of a given end, edge. And so what Glauber dynamics does is, as I said, like this matrix sigma is choosing one of those sites uniformly at random. And then what gamma does, it will just check the value of the spins neighboring that one spin on the, say, on the kth site. And depending on how many spins are aligned with the one on k, minus how many are not aligned on k, it will decide with a certain probability to flip the value of the spin on this side. Okay? So you can actually check that, again, this gamma matrix can be rewritten in the case of this Ising model as a function of EY minus EX. So it's very similar to what we've seen for Metropolis. The main difference between Metropolis and Glauber is that you will, at each step, only flip one spin at a time. So you will not have global updates. You will only have local ones. Okay, so you can again plot this, this matrix gamma xy as a function of EY minus EX, and you see that, again, you are very highly biased towards jumping towards lower energy configurations. So it's very similar to Metropolis in that sense. And again, this gamma matrix is chosen so that you know that the detailed balance condition is satisfied. All right, so this is enough for classical MCMC, and let's see how we can actually find some quantum extensions of these ideas. So here, a naive guess would be to just replace distributions by states and transition matrices by quantum channels, or completely positive choice preserving maps. So we have to find one of those CPTP maps that, first of all, should fix a given Gibbs state. Okay, so this is the first requirement. And again, we would like to have some good properties for those methods. So the first one is that you only fix one state. So you know that you converge to a unique equilibrium state if you apply this CPTP map many, many times. And what would be very convenient would be also to restore some kind of detailed balance condition also in this quantum setting. But if you look at the way I defined detailed balance earlier on, it was highly depending on spin configurations. So now in the quantum case, since we don't have a natural way of defining an underlying basis, we have to find some basis-free manner of redefining this rule. And we can luckily already do this in the classical case. So classically, what you would do would be to consider some distribution-weighted L2 inner product between functions of your configuration space. Okay, so you're taking the sum of function f bar of z times g of z, and you weight this with the actual weight corresponding to your distribution. And then using this inner product, you can show that the detailed balance condition is equivalent to this condition. And when you apply your transition matrix on the left, so on functions, it should be self-adjoint with respect to symmetric with respect to this inner product. So the way you can verify that this is true, so this is equivalent to the previous definition, is so to go from the right to the left here, you just choose f and g to be Dirac functions on x and y, and you directly recover these conditions. And from left to right, you just use the sesquilinearity of those inner products together with the fact that you can always write any function as a linear combination of Dirac functions. Well, they form a basis. OK, so now we have a nice basis-free manner of defining detailed balance, and let's see how we can extend this to the quantum setting. And so I already mentioned before, so in this classical setting, when you look at this symmetry condition for the transition matrix P, I'm thinking of it as applied on functions. So in the quantum sense, I would want to think of these transition matrices, or these channels, as being applied on observables. So I have to look at the dual picture, the Heisenberg picture. So I'm looking at P dagger as my Heisenberg dual to my CPTP map. And I will impose that it is symmetric with respect to some state-weighted trace inner product. You have the choice of which inner product you would like to take, but the one that seems to be the most fruitful one is the following one. So it's the Kubo-Martin-Schwinger inner product, or KMS inner product, where you're weighting your trace here with half of the state on the left of your observable X and half of the state on the left. All right, so let's now try using these ideas to actually come up with quantum Gibbs state preparation algorithms. And the first thing we would like to do would be to find a way to extend Metropolis to the quantum setting. And here we'll make one further assumption that is, again, highly unphysical, but will turn out to be very useful, namely that the Hamiltonian is non-degenerate. So for any energy eigenvalue, you have a unique eigenstate associated to it up to a phase. OK? And one first thing that you can realize is that you can actually, without loss of generality, assume that the system is initialized in any of the eigenstates of your Hamiltonian. And one way you could do this is just by using quantum phase estimation once again, right? Because by what we saw here, what this algorithm does is it selects, if you have some states, some arbitrary state that you can write as a linear combination of eigenstates, for each of those eigenstates, it will just label the energy corresponding to it. And then if you were just to measure this energy label, you would actually have prepared some eigenstate with some probability. OK? So with that loss of generality, then we will assume that this chain is initialized in some eigenstate. And now the idea or the question is, can we figure out some map P whose actual action on my eigenstates would be to just mix them in a way that, that is ruled by this transition matrix, some classical transition matrix. All right, so let's think about how this was done in the classical setting again. So the classical Metropolis algorithm was the contribution of two ideas. The first one was arising from this sigma matrix, which was initializing some jump from X to Y. And in the quantum setting, the way to actually perform a jump would be to just use some random unitary matrix on your system. And for simplicity, I will assume that this unitary matrix is going to be just a single qubit Pauli jump. So you just choose uniformly at random one of your qubits, and you choose uniformly at random one of those sigma X, sigma Y, sigma Z, and you just apply this to your system. Okay, so this is not the only way you could do this, but this is just to fix ideas for now. And then if you think again about what Metropolis was doing, it had to compute the energy of your system before and after the jump, and depending on the difference, it would either perform the jump with some probability or not. In the quantum setting, you don't want to just measure the system, because this would actually perturb it. So what you would do instead would be to use, again, quantum phase estimation to coherently gain information about the energy of your system. So you do this before the jump and after the jump with two different energy registers. So mathematically, what you end up with is the following state at the end of this last quantum phase estimation, which would be a linear combination of system eigenstates labeled by the energy before and the energy after. And the amplitudes here will be nothing but the amplitudes corresponding to your Pauli matrix that you chose in the eigenstate eigenbasis of the Hamiltonian. OK? So then now you have to choose whether or not you actually want to perform the jump. So for this, you append one last system, a qubit system that you initialize in the 0 state. And then you will coherently, essentially looking at these energy registers, decide whether or not you want to jump. And this will be done by applying some controlled rotation on this last register. So this is the state, sorry, this is the state that you have, some 4 pi state. linear combination between 0 and 1s on the last system for each xy. And then you measure this last register. And let's say that you measure 1. So you are actually, in this case, in an accept situation. So you want to accept your transition to psi y. So for this, you will just measure the last register here, energy register. And depending on which energy epsilon y you get, you know that the state you end up with will be collapsed into psi y by construction. And this will happen with a probability that is again given by this Hadamard product between some sigma matrix and some gamma matrix, where sigma here for us will be the square, or the coefficients of sigma will be the square amplitudes of x of the S Pauli matrix. Okay, so it seems like up to here we have managed to exactly follow the classical metropolis rules. Now let's see what happens if you want to reject the jump. So in this case, you would like to go back to the initial state, psi x, that you started with. But now in this quantum setting, things become a bit harder because you have performed some measurement here. And so you would need to potentially undo it. And this is not something you can do just unitarily. So you have to come up with some clever ways to do it. I don't want to discuss this here, but there is some way you can actually undo this with some high enough probability, and which means that you could, in a way, go back to this state psi x here. Okay? So assuming that this last fuzzy thing actually works, then what you have managed to do is to show that starting from some state psi x, some eigenstate of your Hamiltonian, you have found some process which probabilistically chooses between eigenstates psi y with probabilities given by some transition, some classical transition matrix, which is once again given as the Hadamard product of some two contributions that really look like the ones that we have seen in the classical setting. Okay? So because of this, and if you choose this gamma matrix exactly like in the classical metropolis setting, we know by construction that the classical detailed balance condition will be satisfied when you think of those eigenstates as your classical configuration space on which you are mixing your states. Primitivity is something you can also easily impose. Typically, if you choose all single qubit Pauli jumps, you know that your chain will be primitive. So you know now that with this method, this algorithm actually converges to your Gibbs state. Okay? So I actually put a lot of things under the rug that happen to be very important here, which I just briefly want to mention. The first one is that this whole process hinges on the fact that you can actually perform exact Hamiltonian evolutions, which is something you can actually not do in practice. What you would do in practice would be to find some discretization of your Hamiltonian evolution, and this will endure some accuracy costs, which you have to take into account. The other thing, of course, is that, as I mentioned before, energy eigenvalues are not going to be always necessarily described with only r bits of precision. So in practice, you have to find some way to round off your error. And this will, again, cause some accuracy issues. But you could also say at this point, well, this is also something that happens classically, right? Classically also, you don't have necessarily energies that can be written with r bits. So maybe this is just the same thing here. In fact, it's not quite the same thing here, because if you think about where these issues, where this rounding off issues happen, they happen in the quantum phase estimation algorithm. And what quantum phase estimation does, if it doesn't have access to the exact energies, it will just output some energy label with a certain probability that will be picked around that one label whose value is the closest to the actual energy of the state. But it will be giving you a process that is not deterministic any longer. So it gives you like some probabilistic way of choosing some energy. And this is something that actually makes the whole analysis of the algorithm much harder. So you have to find ways to amend those issues. And I won't discuss this further because there will be a talk about this next week, so which I'm very much looking forward to attend as well. All right, so instead of doing or pursuing this route, let's try to do things slightly differently. Now we'll consider my initial jump operators Sk. And I will rewrite my jump in a slightly different manner. So what I will do is I will first take the time evolution, so the Hamiltonian evolution on this Sk, and then I will integrate this against some function, which I will choose to take as the Fourier transform of function gamma, which turns out to be the amplitude corresponding to this gamma matrix evaluated at EY minus EX. Okay, so this may look a bit odd at first glance, but we will see actually that it's a very useful way of writing our transition matrices. So this is what we had already before. And now you can rewrite this product in the following way. So you look at the overlap of this new time-integrated party jumps between sandwich between psi x and psi y, your eigenstates. So what happens here is that when you plug psi y on the left and psi x on the right, you see that you are touching in the integral here these Hamiltonian evolutions. So you will actually get some phases there. So you have EY here and EX here. And then the time dependency of this integral becomes just a scalar, so you can integrate over this. And so what you get is nothing but gamma, the function gamma, evaluated at EY minus EX when you perform the Fourier transform. And since you do it in two steps, you do it here on the left and here on the right, you have a square. Okay, so by this, you have managed to reform the gamma matrix here. And what you're left with then is, again, the overlap of your eigenstates in the initial Pauli jump. Okay? So if you square this, you also get this other contribution to my transition matrix. So what have we gained by doing this? Then we can rewrite this whole transition matrix as an overlap between some evolved state, psi x, according to this CP map, whose cross operators are nothing but these time-integrated party jumps, and psi y, the state at which you may want to jump. So what is nice about this way of writing the algorithm is that now I have a basis-free way of understanding my jumps. So potentially I can even, at this point, forget about these issues coming from having to assume that energies can be written in a certain way and so on. And we are lucky here because if you choose these gamma functions in a suitable way, then you can even show that the quantum detail balance condition is satisfied. So we are getting close to the goal. But there's still one big issue that we have to take care of, which is that these CP maps are not trace preserving. So they don't actually define proper quantum evolutions. All right, so let's see how we can amend this issue. And for this, let's go back to the classical setting and see how people can think about MCMC methods in a slightly different way as well there. So we have already described a MCMC method, which is a time-discrete evolution or process, where at each step, deterministic step, you're applying this transition matrix. But you can also do it slightly differently by assuming that between each of your applications of this jump, you wait for a random time, which let's say you take to be distributed according to the exponential law of a parameter lambda, and each of those intervals being independent from each other. Okay, so you just wait for some random time, and then you apply your jump, you wait again, you apply the jump, and so on. And then once you have done this, what you actually created is a Poisson process for your jumps, whose law can be described in the following way. So assuming that you start your chain and some configuration x, then the probability that your chain happens to be in configuration y at time t is given by the xy coefficient of this exponential matrix. So what you have actually done here is to rewrite your new continuous time process as a semigroup of classical channels, which is generated by some matrix L here, which in this case is lambda times p minus identity. So this new way of writing things in terms of continuous time processes actually keeps all the important properties you would like to have. So first of all, the detailed balance condition is still satisfied, because if you know that P is symmetric with respect to some inner product, then P minus identity will also be, so hence also the evolution. So you know you converge to the right state. And then this gives you a new way to think about those methods. So how can we now use this to solve our issue of normalizing our CP maps? Well, luckily for us, people have done a good job before, and they have found some way to characterize generators of quantum, semigroups of quantum channels. And those generators, which are also known as Lindbladians, always take the following generic form. So forget first this contribution here. Let's just look at the commutator. This is just going to be a Schrodinger equation, but written in this open system sort of setting, where you look at mixed states. So B would be just some Hermitian matrix, which you can think of some Hamiltonian, which may not be the one that corresponds to the Gibbs state, but can be some other Hamiltonian. And then to this coherent contribution, you can add some dissipation terms, which can be always written in the following way. So you have some what we call Lindbladian jumps or Lindblad jumps of matrices L here. And this contribution, which depends on this matrix L, is itself the sum of two terms. One that is a CP map generated by this cross operators L, and some other contribution, which is just the anti-commutator of L dagger L with the state. So this anti-commutator is what extends or generalizes this minus identity in the classical setting. So essentially, once you look at quantum systems, you have more freedom to define generators, but you see that they're reduced to the previous setting. And the nice thing about this construction is that this CP part does not require to be, we don't require it to be trace preserving. Okay, so the intuition here is then to simply pick as your Lindblad jumps exactly some normalized version of your time-integrated Pauli jumps. And we hope that with this definition, finally we have found some process that converges to your Gibbs states. So here is the generator that we will consider. And let's see if all the assumptions we want to satisfy are actually satisfied. We still have one issue. So I told you before that this CP part is in detail balance. However, it turns out that in high generality, the anti-commutator part will not be detail balanced. So you lose symmetry by adding this anti-commutator part. And however, and this is, I think, the genius idea that came up out of this paper by Chen, Castorian, and Gillian, you can actually use or choose the Hamiltonian part here, the coherent part, in a clever way to ensure that the sum of this anti-commutator and this commutator parts together will retain symmetry. Okay, which means that the whole generator here will still be KMS symmetric, so detail balance is satisfied. And okay, I won't spend too much time into how you construct this B part, but there is an actual expression for it, and you can check that with this definition, then the whole thing is KMS symmetric. So detail balance is satisfied. Primitivity is still there. And by construction, we have a generator that actually generates a semi-group of channels. So we also amended this normalization problem. So we have everything we want now. We know that we have some evolution that eventually will converge to our Gibbs states. So at this point, maybe one question for me. Do you think that this is enough for us to be happy? So there's still one issue.
Yeah, I don't understand how so you have to put in B, but B has sigma in it, right? That sigma is the target state, or what was sigma?
Yes, sigma is the fixed point, but you're right. But I can actually show this is not a big deal because the way that sigma appears here will be only through the exponential, and this one you assume that you can efficiently know. So there will not be any partition function in this
Okay,
in the B
thanks.
part here. So essentially, the only thing you need to be able to do here is to perform Hamiltonian evolution to construct B. So that's fine. So I don't know where you are, but yeah.
Hello. In the quantum detail balance condition, you have sigma in the formula itself, like unlike the case of classical detail balance. What is the intuition behind having that sigma, and how do you check it when you actually don't know what sigma is?
Yeah, I'm not sure I understood the question.
I mean, how do you verify that quantum detail balance in your algorithm is satisfied when you actually don't know the thermal state?
Oops. Sorry. I mean, so the idea is that you know what the Hamiltonian is, right?
Yeah.
So mathematically, you can verify detail balance.
Without knowing the thermal state ahead of time.
I mean, you have a mathematical description of the state that you want to prepare.
Okay.
That's part of the problem, yes.
Thank you.
Hi. What is T Gibbs for these metropolis-based algorithms? I didn't see T Gibbs that you told that earlier that purification-based algorithm you told that it is global speedup, but what about these algorithms, that metropolis or this operator?
Sorry, I'm not sure I understood.
That T gives time that the cost of this algorithm.
The cost?
Oh yeah, the cost.
We will discuss it in the next session. So far, I don't say anything about the cost. Yeah, that's right.
Hello.
Ah.
Hi. So actually, it has been documented before that if you use an open system evolution with a certain generator, it is not always going to lead to a thermal state unless a generator follows certain conditions, which are known as like Davis conditions. So how do you impose that in this setting?
To impose which conditions? You mean the primitivity condition?
Like,
or
no, like essentially Davis generator conditions. So how do you impose that in this particular setting?
the which conditions? Sorry.
They are called Davis generators, Davis conditions.
So these are not necessarily Davis generators. I will tell you later that actually they define a family that is larger than Davis generators. So Davis generators are incorporated within this family, but are just one single instance of it. So you don't need to satisfy the Davis conditions here to still have an evolution that converges to the state you care about.
Could I just check what goes wrong if we use an algorithm over here? If we use an algorithm that doesn't satisfy detailed balance?
So there are some candidates that also do this, but there you have to find a way to ensure that the state you converge to is somewhat close to the actual state you want to prepare. And for this, typically we need to know what's the time it converges.
I see.
So you need to have some more assumptions on your system.
Right, okay, thank you.
Yes?
Hey, I just had a question. In practice, when you implement this, would you do it on some sort of annealing architecture or an actual digital architecture when you evolve this thing?
Actually, this is great because that's, later. It's directly related to what I want to discuss now. So there's still this issue, we don't know how to implement this yet, right? So we have to think about this, yes. Any other, yes?
I guess, are there any like physical limitations for Fourier transformations in like crystalline structures? I work specifically with like chain crystals and carbon crystals. Would applications in like Qiskit models like would there be any like would there be any physical limitations or?
I think I'm not the right person to answer this.
Okay.
I don't have a good physical knowledge.
Right. Thank you.
But I can imagine there would be some issues here.
I'm sorry, I think you mentioned something about non-degenerate eigenstates as a requirement to begin with.
Yeah.
So if the Lambdatian is like not gapped, then do you not just like it won't work, right?
So at this point, once I arrived at these Lambdatians, actually I don't need this assumption any longer. This was only to describe this metropolis type algorithm, but now I don't need this anymore.
Okay, cool.
Yeah. Okay. So going back to your question, then we still have to understand how we can actually implement this on a quantum platform. So there are different ways of implementing Lambdatian evolutions. I just want to give you one construction which I find very simple and neat, which is due to Li and Wang. So the idea here is, okay, you have some generic Lambdatian, which is defined in terms of some coherent part B and some Lambdatians L. And I will rewrite this Lambdatian in a certain way. So I first look at the CP part. I take it on its own, and then I take the commutator and anti-commutator parts together, which I will call a drift part. So the drift part will be given as a function of some matrix G, which you can write in the following way. So the way you can think of this G matrix is what it will do on your underlying Hilbert space is it will generate some non-Hermitian evolution. Okay, non-Hermitian because you have the sum of these L dagger L's that are there. And I want to think of the CP part now as some sort of perturbation of my drift part. And what I mean by this is that you can use some expansion, some Duhamel expansion, of the time dynamics generated by L, where to the zeros order, what you have is just the time dynamics generated by your drift part. Then the first order would be some time integral over the composition of contributions coming from the CP part and contributions coming from the drift part. And then you have, of course, higher order terms, which will just be multivariate integrals of compositions of those components. So from here, you see that if you had a good way to implement both the CP part and the drift part independently, then you would have a way to also implement the whole evolution. And here, the way that you can implement, let's say, the CP part is by means of a very useful algorithmic tool, which is known as block encoding. So what we want to do here is to find a way to apply some non-unitary matrix on a pure state, say one of those jumps L. So this you cannot do on its own, but the way you can do this is by thinking of L as being some upper block diagonal part of a bigger unitary matrix, UL, which we call the block encoding of this jump. As long as you can always do this as long as you normalize this L suitably. So you have some normalization factor SL associated to L. And so the way you can think of what this block is doing on your system is you append to your state some further register whose dimension will be directly related to the dimension of this matrix UL. And then on the joint system, you just apply this block encoding, and then you project your ancilla on the zero state. Okay, so this is exactly a circuit description of what this matrix is doing. And then you can check that if once you project it onto the zero, what you have is nothing but L over SL applied to psi. Okay? So this is a non-deterministic way of implementing L on your system. And so once you have, let's say that we have access to those block encodings for each of those jumps. And let's say you want now to actually implement the CP part. So you have many jumps, L, and each of them is coming with its own block encoding. And to implement the CP map, you append a further third register initialized in some linear combination of orthonormal bases that label your jumps with coefficients that are nothing but the normalization factors for each of those jumps. And then what you will do is you will implement this block encoding controlled by this last register. Okay? And then once you project again on the first register on the zero state, you can check that the state you have actually generated on the last two registers will be a coherent implementation of your CP map, where you apply L on the state psi, and then you also keep track of which L you have applied on the third register. Okay, so if you were to then discard this last system, what you would actually have is nothing but the CP map acting on the second register. Okay. So then if you do this and you do something similar on the drift part, which I won't explain here, you can show this kind of results. So this one is due directly to Li and Wang. So they show that if you are given access to these block encodings for each of the jumps as well as for the coherent part B here, then you can use them into constructing a dissipative quantum circuit for each time t, which will get epsilon close to the actual time evolution in diamond norm. And this circuit will require a number of queries to these block encodings that will scale linearly with the time that you're trying to achieve. And further single and 2 qubit gates, whose number will also scale linearly with this time parameter, as well as with the number of jumps that your CP part is constructed from. Okay, so this gives you some way to efficiently implement your time evolution. So what have we gained by this? We actually then, what this means is that we reduce the question of how we could implement these Lindbladian evolutions to the question of how we can implement our actual jumps, which for us are these time-integrated versions of Paralys, right? So if we know how to implement or to find some block encoding for those guys, then we know how to implement the generators. So let's think about how we do this. And so this is, again, the expression that I had given to you before for these time-integrated Pauli jumps. And now if I assume that this weighting Fourier transform gamma hat here is very nicely behaved, so typically I want to assume that it's rapidly decaying at both infinities and smooth enough, then this time integral, you can always approximate it to good accuracy by some discrete sum, okay, some quadrature. which here I take to be some Riemann sum, but you could do something more clever to get better accuracy. And so this discretization will just give you the same coefficients you have in the integral times the time step, corresponding to the time at which you want to apply those unitaries, and then the product of those three unitaries. Right? So now the question is, how do we find some block encoding for these discretizations? And for this, you have to use well-known methods for implementing linear combinations of unitaries. So what you could typically do is to, again, have your system, first register, second register, initialized in some, let's say, time state, which is a linear combination of orthonormal basis states which label the times at which you want to perform your jumps. And you initialize the system in the state whose amplitudes are the square roots of those parameters here in the sum. And then you run a product of three matrices. First, some controlled time evolution at time tm, okay, which implements the first part here. Then the Pauli jump, which implements this guy. And then the reverse time evolution. Okay? And then if you further project onto the same state that you started from, you can show that on the system register, you actually have implemented your approximation of the time integrity jump. Yes? I think it's better today. I've been told it's better.
So for the time register, does the amplitude of whichever state, you said it's like non-zero, and then the amplitude of the times you want to implement this thing are non-zero. Is it arbitrary? Is it uniform over those states?
For which, sorry, for?
So the time register, right, it's controlled on the times that you want to implement this thing. But what is that time register look like? Is it all zeros except a uniform over the times that you want to implement, or is it just one time? Or
these are orthonormal basis vectors, right? So depending on how many time steps you have, depending on the discretization that you have, the accuracy you want to achieve, this register will be larger and larger if you want to have better accuracy. And then you just have to implement those states.
I see. Thanks.
Depending on the accuracy, yes.
Thanks. So do you have some, say, estimation in terms of depth and ancilla number, like depth of 2-qubit gates or so for such a, implementation of the evolution?
So I will give you in the end the actual gate count for the whole thing.
Right,
but here, it will just depend on how well you want to approximate those things. But yeah. So it's actually what you get in the end here is. So if you actually do the gate count, you will get an algorithm that approximates your evolution to epsilon precision, which would require total amount of Hamiltonian evolution time that will be scaling linearly with the time that the target time that you're trying to achieve. And then you have further single and 2-qubit gates, which will also scale linearly up to some polylogarithmic factors, but it's essentially linear in time. There was another question.
A tiny question. So does Tm scale linearly with M in the equation, or do you, because you mentioned you use the word time step, so.
Okay, so time for me is maybe it was not the right way of defining this, but it's just telling you this is like a time discretized version of the integral here.
Right. So to discretize it, does Tm scale linearly with M? Does that can be generalized to arbitrary?
You mean for how you actually do this approximation? So here I just used Riemann series. It would be linear, but you can do Gaussian quadratures, and it will give you better.
Oh, I
better
see.
estimates.
Okay. Thank you so much.
One more. Do you have any estimate on the mixing time? You have mentioned it, right?
So far, what I mean by efficiency is really just that I know I can implement up to time t, right?
Yeah.
But I haven't mentioned the mixing time yet. This will be the next important question I have to assess. Okay. At this point, I just want to have a way to implement those evolutions. But I haven't told you whether or not they converge.
Kind of going off of what previous gentleman said, I know we're talking about timescales later, but do you know if as the system increases in size, will the timescale decrease linearly or logarithmically?
The time scale for what exactly?
For the processing of the model.
You mean for
Yeah.
the implementation of the state?
Yes, implementation of the state.
It would depend very much on your system. So there will be systems for which it will be linear and some systems for which it will be exponential.
All right, thank you.
Okay. If there's no other questions, then yeah. So going back to the actual cost of implementing those maps, one thing I also want to mention is that, of course, I gave you the cost in terms of Hamiltonian simulation times. So that also again tells you that if this would be efficient only if you know that you can efficiently implement your Hamiltonian evolutions. But if your Hamiltonians are nice, so if they are like sums of local terms or sparse matrices, then you have actual efficient methods to do this. So. Okay, so I'm just given, I think, 10, 15 more minutes to discuss how we can think of this last algorithm I've described to you as one way to mimicking what we believe the actual thermalization process occurring in nature does. And so now let me try to think about these evolutions in a physical manner, starting from some microscopic description of your system. So what you would typically think about is that your system at time equals to 0 is put in contact with some very large environment, or some bath, which is a coffee cup here. And so the way that you define the way that these two systems will interact will be by means of, again, some big Hamiltonian, which will be the sum of 3 contributions. So the Hamiltonian H, which is nothing but the one that we've seen until now, so the one that describes the interactions within the system itself. HB, which is the Hamiltonian describing the interactions within the bath. And then some HI here, which describes interactions between particles of the system and particles in the bath. And then here I want to assume that those last interactions that couple bath particles and system particles is very small. So I want to think of a very weak coupling between the system and the bath. So by this I mean that I will weight this Hamiltonian here by some delta, which I want to think of being very small. Okay? Then I make the system and the environment evolve together. So I have some Hamiltonian evolution on the joint system. And then I look at the reduced state on the system at a certain time. So this is the actual microscopic description of my evolution on the system. And now, so Davis in particular, which we already mentioned before, realized in the 70s that if you now take the limit of a very, very small coupling, so this delta going to 0, and at the same time you rescale the time parameter in this diffusive manner, then essentially what happens on these evolutions is that they will converge when delta goes to 0 towards some evolution that will be generated by some Lindbladian, okay, which is called Davis Lindbladian. And it turns out that this Lindbladian is only one instance, as I was saying before, of this class of generators I have described before. So if you were to take this gamma function, this gamma hat to be 1, independently of t, this would actually give you back Davis generators. Okay, so this means that by our constructive, the way that we constructed the algorithm is not too far from what nature does. So we can hope that whenever nature can simulate or can prepare Gibbs states, then we could also prepare them using our methods. And because we had access to Davis generators since the 70s, people have not waited for these new algorithms to actually describe how fast it takes to converge. And Davis generators were used extensively over the last years to better understand the potential properties of a quantum system for being a good self-correcting quantum memory device. Okay, so by this I mean that this would be a device on which you can actually encode some logical quantum information. And the hope would be that you don't need to do anything for this logical information to stay within the device for a long time. And so your ability to know whether this is the case will be directly related to the time it would take for the system to thermalize, meaning that if it thermalizes fast, your guess is that the logical information is actually lost at very quick times. If it thermalizes at very long times, then you can hope that you keep the information for also a long time. And so typically using these generators, people have shown that for the so-called 4-dimensional toric code, that Hamiltonian, So that CSS code is thermalized in exponential time, so exponential in the number of qubits in the system, meaning that it's probably a very good self-correcting quantum memory. And on the other hand, the two-dimensional Turing code, which we know to be a very good model for error correction, where you have to actively error correct for whenever something happens on the device, this one will not will only converge into the Gibbs state in polynomial time. Okay, meaning that it's actually not a good model for self-correction. Okay, so I will also not say more about this because, again, there will be an interesting talk on this topic next week. So you will learn more about this later. Okay, so I think I'm done with this first session. If there's no other question, then we can resume later. Oh, there's one here.
So I know you said you weren't going to talk about it, but quick question about it. In, I think it was quantum phase estimation, or no, sorry, it was Metropolis, the reject step. When you measure it, don't you lose the eigenvector that you prepared? So do you have to waste all that time to prepare it again, or?
You're not so you can recover it with very high probability, but you have to do something very clever there.
Okay.
So my question was, what's the difference between that self-thermalization, self-correcting memory? What's the relationship between that and topological quantum computing? Is it the same thing or is it different? Because topological quantum computers are also supposed to self-error correct, right?
I'm sorry. The connection to topological quantum computing. I'm not sure exactly how would be the connection, to be honest.
Okay, so it's not the same thing. They're different things.
Sorry?
Self-correcting memory and topological quantum computing are different things.
I would say so, yes.
Okay.
I'm just curious, in practice, for this algorithm, can it be useful at the NISQ era stage, or do you need fault tolerance?
It's very likely you need fault tolerance for this, because you saw that there was this, you have to correlate or entangle your system using all those control registers, so it's very unlikely you can actually perform this with the current devices we have.
Would you mind going to the previous slide?
Sorry?
Could you go to the previous slide for a second? Yeah, when you were setting up like the sampling algorithm, you mentioned that like the operators that you use in your Lindblad equation, they don't have to be physical. Like they don't have to be, if you're trying to model some real system, they don't have to be the actual Hamiltonian or the actual like physical jump operators. Do you expect that for systems of interest, I guess, you could design operators that converge to the fixed point faster than you would see in nature? Like, that is faster than the natural Hamiltonian.
So I wouldn't have an actual mathematical proof of this, but that's the hope, that if you choose the jumps correctly, then maybe you converge faster. One typical thing you would like to do here is so here I only looked at single qubit jumps. Every time I was just applying these single qubit Pauli matrices. If instead of this, I was applying global jumps, which I can do, I can still have a block encoding of those guys. Then we know from, let's say, the classical intuition that this actually can help you in converging faster.
Thanks.
In the MCMC method, so basically what you're trying to do is to replace the classical random walk on a graph with the quantum walk, right? So usually, I mean, I'm not a specialist of quantum walks, but usually there is no measurement during the evolution process, and you only have unitary evolution with the coin flip and swap
It's a very
operators.
different kind of walk, yes.
And doesn't it worsen the runtime to have measurement inside of the evolution process? Like, do you still get this quadratic speed up on?
No, not if you do it in this way, but you can also purify this type of evolutions, and then you would actually get back the square root speed up also those ones.
Hello. You mentioned quantum weak samplers on analog quantum simulators. Does quantum Gibbs sampling works more naturally on analog computers? Would it work more naturally, or it's?
I think it's a very interesting direction, but I don't know of any people who actually took this very seriously, at least in the theory. It would be nice to see whether we can actually use this as a non-universal model.
Is there a specific interest in running quantum weak sampling on an analog quantum computer?
I would say so. Yes. Yes.
Okay.
Hi. Should I go ahead? Hi.
Oh, sorry.
So this actually concerns the part of the transition matrix which simulates only local Pauli jump. I've seen that if you were to map all of this in configuration space, and if you have local Pauli jumps, then you are going to create configurations which differs only by 1 unit of Hamming distance every time, right? So that can actually slow down mixing time by a lot, because you might be stuck in some local minima and you are not going to actually sample the whole space quite efficiently. So do you have any thoughts on doing like cluster updates on or global updates instead of local updates?
So you could do this, right? I mean, here I use those single qubit polygons just for simplicity, but you could just use anything that you can block and code, so this would be fine when it comes to implementation. But I guess the question is more like, does it fasten the convergence?
And also not, like say for example, if we replace the Pauli jumps with some other gates, we'll have to ensure that that part of the transition matrix is also aperiodic and irreducible. Otherwise, it is not going to converge.
Sure.
Right. So, like, what are your thoughts on these? Like, we have to maintain a set of conditions on the transition matrix. At the same time, we also have to speed up the mixing time. So, what would be the best set of like cluster updates beyond local Pauli jumps that you would suggest?
Okay, my first guess would just keep the single qubit polymer, wants to ensure that you are still primitive, and then just add some other on top of it. That would be one way to have both. Yeah. But I don't know what, like, theoretically, I don't know how you could show fastening.
Hey, you mentioned the classical optimization and SDPs. So in the case of diagonal Hamiltonian, is it correct to say that this is just the same as classical Markov chain, or does it get to something better?
Sorry, can you repeat this?
Yeah, in the case of a classical Hamiltonian, like a diagonal, so does it just the same as classical Markov chain Monte Carlo, or does it get better in some?
So you mean when it comes to SDPs only, or in general?
Yeah, in general, SBs as an example.
So you would hope so that if you add jumps in other basis elements, then it should go faster. But actually, you can show that at least in general, it will not be the case. So you cannot improve for any Hamiltonian. You will not be able to improve.
So these methods are not relevant for SDPs or classical optimization. Is it what you say?
Well, I mean, they will always give you some runtime, right? So I'm not sure I'm understanding the question, but you mean, do they get better than the ones that I showed you before, or?
My question is, does this method, for example, is better than like classical Gibbs sampling for classical problems?
In general, I would say no, but then you have to look at the specific matrices you're looking at, or the specific system you're looking at.
Thanks.
Hi, sorry. Could you briefly explain again how you ensure that this Lindblad evolution converges on the Gibbs state, and how you impose that? What conditions you need to impose on the jump operators to make sure that this happens?
So you have this KMS condition, this symmetry condition, which remember the fact that the generator is self-adjoint with some inner product.
Right.
So this ensures that you actually fix this Gibbs state.
Right. So it's just from that, from fulfilling that condition.
This together with this primitivity condition,
right,
which tells that you have unique fixed points. So you know you will converge to this one.
Right, okay.
If you had multiple fixed points, then you could just converge to any of them.
I see. Okay, thank you.
Sorry, so we know that at low temperature limit, we expect the Gibbs state to approach the ground state.
Mm-hmm.
So you propose an algorithm, well, you discuss an algorithm that prepares the Gibbs state. So do we anticipate that at the low temperature limit, this algorithm also to be a viable algorithm to prepare ground state? And how does it compare in terms of like time complexity to the current existing algorithm to prepare ground states?
So it will anyway in a general setting be exponential because we know that preparing ground states is extremely hard. Whether you can find speedups, then I think it's unclear.
Okay.
Yeah. But we'll discuss this later in the second session.
Hello. How will the machine kind of alter during if it reaches Bose-Einstein condensate like temperatures? Will the algorithm like change, or would it like respond to the extreme temperatures?
Would we? Sorry, can you repeat that?
I'm talking about Bose-Einstein condensate like materials, and if the qubit, if the qubit is like at that temperature, would anything happen to the algorithm? Would it change, or would it just correspond to the temperatures? Or is that more of a physics-y question?
Probably better, yeah. I wouldn't know how to answer.
Okay, we'll take one last question if there is one. Okay, so, okay.
I'll make it quick. How well do you think the Davies generator approximates what nature is doing when it's thermalizing?
Can you say again?
How well does the Davies generator approximate? Like, do you think the Davies generator approximates how well nature is thermalizing?
The
like
Davies generators, how well they thermalize, or?
How well does it approximate what nature is doing? Like, do you think?
Yeah, that's a good question because you can actually show for these many body systems that your Davies generators will actually be non-local, so they are not physical in that sense. But the nice thing about this other set of generators is that they are local if the Hamiltonian is local. So you could hope that this is kind of what nature does, right? It keeps locality. The dynamics is still local. So, yeah. Actually, you can show that this approximates well. If you think of this way of writing the microscopic evolution in terms of this reduced state dynamics, you can show under some conditions on the environment that this will be very close to the actual invariant dynamics.
So let's thank Cambyse. So we'll have a 30-minute break and we will start at 11 again. So I think there are refreshments outside.